So we're in chapter 19 now, Dr. Balmester's Physics 2 class. We're studying the first law of thermodynamics. What is thermodynamics? Yes, so first we need to know some basic definitions. A system characterized by its pressure, volume, and temperature only. If you had these three, that gives you the system. We say that this is a thermodynamic system. Another way to put that is to say that the state of the system, of a thermodynamic system, is given by its pressure, volume, and temperature. Thinking of it that way, its state, it has a state space, one could say. You give me the pressure, the volume, and the temperature. Its position in state space would be right here, whatever that pressure, volume, and temperatures are. Sometimes, like for an ideal gas, you have these variables aren't all independent. So you have for an ideal gas, PV and RT. In that case, you just have two independent variables. So maybe I think it's usually, you usually choose P and V, and this will be the state space, right? T is given by the ideal gas law, which is not the general case, but yes, for the special case, this would be the space, state space, two-dimensional. Anyway, changing from one point to the other, moving from one point to the other, some initial state to some final state. This is said to be a thermodynamic process. Of course, you go from there to there along some path or other. Okay, with these definitions, then, the first law of thermodynamics is this. Where U is the internal energy of the thermodynamic system. And it is depends only on the state. So that, for example, in which case we can say the change in U is path independent. What does that mean? Okay, this might be a going from this state to this thermodynamic state. That is a change in U. The change in U would be the same whether I took that route, that thermodynamic process, or this one, or any other that has the same initial and final states. Very important. Another thing is the work done by the system. Q is the heat put into the system from the outside. W is the work done by the system, and W is defined as the pressure. Well, we derive this from the definition of W as the work done by the system on the environment. It comes out to be the initial, the final, P dV, the volume integral over the pressure. So with these definitions, then let's look at a problem, I think number 1937 from the text. So 19.37, when a system is taken from a state A, in this picture, to B, along path A, C, and B, this much heat flows into the system, and this much work is done. Sigma work is done in the system. Okay, what does that? How can we make note of that? So we go from A to C to B. Taking this route, we have amount of heat added to the system. I'll call that Q1. That is 85, they say. And the work done, work 1, taking that path, is 60. How much work flows into the system along the path A, D, B? Now for A, D, B, that's from here to here to here. We're getting to the same place, but taking a different route. The work done by the system is 13 joules, so the work to, call it that, is 13, and they are asking how much heat flows. So given that Q2 then is what? We have, that the change in the internal energy is path independent, so we have the change in the internal energy going from A to B. Along the two paths are the same, so we have taken along one path, Q1 minus 1 minus W1, and that is Q2 minus W2, and we can solve this for Q2, looks like what we're looking for. That is Q1 plus W2 minus W1, and what is that? 85 minus 60 plus 13, and that's 38 joules. So Q2, 38. What else? When the system is returned from B to A along the curved path, along this path right here, the absolute value of the work done in the system is 39 joules. Okay, does the system absorb or liberate heat? And the question is, how much heat? So what do we have there? We have that the change in internal energy is Q3. I'll call that the this path right here is path 3 minus W3. And we have W3. What about the change in internal energy? This is the negative of the change of internal energy and going from A to B. And so that on the left-hand side, that should be, instead of 85 minus 60, like before, that is 60 minus 85 is equal to this in W3 we have. So Q3, thing we're looking for, is 60 minus 85 minus 39, is that right? Yes, so minus 64 joules. Heat released in going from B to A. And let's see, so part C, if the internal energy here is 0 and the internal energy there is given, find the heat absorbed in the process from A to B and going from there to there, and A to D and D to B. So let's see if we can get that from what's given. We have that the change in the internal energy going from A to D by definition, UD minus UA. So just UD given, which is 12. What else do we have? That the change in internal energy going from D to B, that is going from D to B, that's one of the heats we're looking for, dB minus the work from D to B. What is the work going from D to B? There's no change in volume, so the work going from D to B is 0. So this then should be just Q of dB. And let's see. The change in internal energy from A to B, we already have from before. That's sort of given, and that's 25. And that is the internal energy and going from A to D, plus that and going from D to B. So I'll write that as first one of which we have there is 12 plus Q dB. And we can solve this for the heat added from and going from D to B then. That is 13. When we do the algebra, it looks like 25 minus 12. So that is 13 joules. We have that. And finally, what we have, the heat, if we took this path from A to D to B, that's Q A D B. That is the same as our Q2 here, ADB. That is 38. And that's equal to the heat added and going from A to D plus the heat added and going from D to B, there to there, there to there. And we solve for Q A to D. So that's 38 rather, minus 13, or 25 joules. So once you get these definitions, it becomes a question of algebra. So you go through it carefully, respecting the definitions, and you should do fine.